Hello everyone, and welcome to this session on classical electromagnetism. Today, we're tackling a fundamental problem, calculating the force between two charged spheres using Coulomb's law. This law is foundational to understanding how charges interact, which is vital in everything from electronics to the very structure of atoms. Let's break down this problem systematically. First, imagine a simple diagram. Draw two small circles, representing our spheres. Label one as Q1 with a charge of plus 2.0 microcoulombs and the other as Q2 with a charge of negative 3.0 microcoulombs. Now, draw a straight line connecting their centers, representing the distance r between them, which is given as 0.30 meters. Next, let's identify our key variables and constants. Q1 is the charge of the first sphere, which is plus 2.0 microcoulombs. To work with our equations, we convert this to standard SI units. So plus 2.0 times 10 to the minus 6 coulombs. Q2 is the charge of the second sphere, negative 3.0 microcoulombs, which is negative 3.0 times 10 to the minus 6 coulombs. R is the distance between the spheres, given as 0.30 meters. And finally, K is Coulomb's constant, a fundamental constant for electrostatic interactions in a vacuum. Its value is approximately 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. This constant bridges the charges and distance to the resulting force. We want to find F, the magnitude of the force. Now, for the relevant equation, Coulomb's law. It states that the magnitude of the electrostatic force F between 2 point charges is F equals K times the distance of Q1 times Q2 over R squared. The absolute value ensures we calculate only the magnitude of the force, as the direction, whether attractive or repulsive, depends on the signs of the charges. Since we have opposite charges, plus and negative, we already know the force will be attractive. Let's substitute our known values into the equation and calculate the force. F equals 8.99 times 10 to the 9th Newton squared over squared, times the magnitude of the charges of the first sphere, which is negative 3.0 microcoulombs, over 0.30 meters. First, multiply the charges, 2.0 times 10 to the minus 6 times negative 3.0 microcoulombs equals negative 6.0 times 10 to the minus 12 Coulomb squared. This becomes 6.0 times 10 to the minus 12 Coulomb squared. Next, square the distance. 0.30 meters equals 0.09 meters. Now, plug these back into the equation. F equals 8.99 times 10 to the 9 times 6.0 times 10 to the minus 12 divided by 0.99. Multiply K by the product of charges. 8.99 times 6.0 equals 53.94. For the powers of 10, 10 to the 9th times 10 to the minus 12 equals 10 to the minus 3. So, we have F equals 53.94 times 10 to the minus 3 divided by 0.9. This simplifies to F equals 0.05394 over 0.9. Performing the division, we get F approximately 0.5993 newtons. To check our answer, the units work out correctly. Newton squared times c squared divided by Newton squared equals newtons. This is a good sign. The magnitude of 0.60 newtons is also reasonable for microcoulomb charges at this separation. It's not an impossibly large or tiny force. Given the opposite signs of the charges, we confirm the force is attractive. To summarize, the magnitude of the force between the two spheres is approximately 0.60 newtons. Because the charges are of opposite signs, this force is attractive, meaning they pull towards each other. This understanding is crucial for designing electronic components, understanding atomic interactions, and even in fields like material science. Remember that the force is inversely proportional to the square of the distance. Double the distance, and the force becomes 4 times weaker. Also, the force is directly proportional to the product of the charges. This method is universal for finding the force between any 2 point charges in a vacuum, simply by plugging in their values. This problem links directly to electromagnetism and underpins our understanding of how matter behaves at a fundamental level. Thank you for joining me today. If you found this explanation helpful, please consider liking this video, subscribing to the channel for more physics and maths insights, and sharing it with your friends. Don't hesitate to leave any questions or comments below. And if there's a specific problem you'd like me to solve in a future video, you can support the channel through donations. Each month, I'll select a few viewer-requested problems to tackle in their own dedicated videos.